Hey folks, welcome back to the third and final video for this beginning portion of Unit 7. The rest I will do live with you in class because it's a little more complicated. This video will cover topics 7.5 and 7.6. 7.5, we'll get into what the value of the equilibrium constant means in terms of its magnitude. And 7.6, we'll look at what happens to the equilibrium constant when we manipulate an equation by reversing it or multiplying it or dividing it by some coefficient, etc. Okay, so this first one, 7.5, you'll be able to explain the relationship between very large or very small values of K and the relative concentrations of chemical species at equilibrium. Okay, if this is the College Board, content, some equilibrium reactions have very large K values and proceed essentially to completion. Others have very small K values and barely proceed at all. So if you think back to the thermo unit, what does it mean in terms of thermodynamic favorability if a reaction moves forward in terms of delta G? What does the sign of delta G have to be if the reaction moves to completion versus what is the sign of delta G if it doesn't occur much at all? And think about how that relates to K, because we will revisit that. So here's the deal. The equilibrium position. When a system reaches equilibrium, there may be more reactants or products present depending on the conditions of the system. And we looked at that when we did the concentration versus time graphs, that you would see something like this. So this would be reactants because it starts out high. This would be products. That you don't have to have those two lines meet, but they do have to level off once equilibrium is established. So you can have a situation where at equilibrium, the system predominantly still contains reactants versus products, or you could have a situation where at equilibrium, the system contains a lot of product. And we're gonna look at how that relates to the K value. So if you have a large value for K, if you're comparing, various numbers and you are looking at a system that has a large value for K, that tells you that at equilibrium, the reaction is product favored, okay? That doesn't mean that, it means that once it's establishing equilibrium. So once I establish equilibrium, I would tend to have more products than reactants. And that makes sense in terms of how we write an equilibrium expression, that it's concentration of product over concentration of reactant. That if the concentration of product, the numerator, is quite high in comparison to the denominator, then our calculated K value would be quite high as well. Conversely, if I have a small value for K, that signifies that when equilibrium is reached, there hasn't been a large conversion of reactants to products. So again, think of it in terms of how K is calculated. If I have concentration of product over concentration of reactant, and at equilibrium, I don't have a lot of product, but I do have a lot of reactant, my denominator is quite large, that will lead me to a smaller K value. And again, those values can vary wildly. You can have something that 10 to the 53rd power. That would tell you that at equilibrium, I basically only have product. I have no reactants left. But if I could also have a very small K value, 10 to the negative 20th, which means that once it establishes equilibrium, I still have a ton of reactant. It barely did anything at all. Something else you need to be able to do is compare a calculated reaction quotient Q value to a given K value. Because what you need to remember is Q and K are calculated in the exact same way. It's, products over reactants. But by denoting something as having this Q value, you're saying that it might be at equilibrium, but it might not. I'm not quite sure. But once I calculate this value and compare it to the actual K value of a system, I can predict which reaction, the forward or reverse process, would be favored in order to get my system to hit equilibrium if it's not there already. So that's what we're going to look at now. So there's three possible scenarios here. You could have the scenario that the Q value you calculate is larger than the K value that you're given. You could have the Q value less than the K value that you're given, or you could have the Q value equal to the K value that you're given. Okay, so the first situation is if I calculate Q, right? So again, Q would be, concentration of product over concentration of reactant. And I get a Q value that is higher than the K value that I am provided with for that process. These are not numbers you have to memorize or anything. A large Q value means I have a larger numerator than I should, which means I have more product in my system than I should. So if I think about my reaction as being reactants converting to products, and I have more products than I would at equilibrium, that would mean that my reverse reaction would be favored in order to get my system to establish equilibrium. I have to reduce the quantity of product and therefore raise the quantity of reactant to hit equilibrium for that system. It's really important that you understand how to compare Q versus K, all right? And I'll kind of give you what my tiny lizard brain uses to help me out when I'm done going over this. The second scenario would be if Q is less than K. So I calculate my, products over my reactants. So here's my equation, right? And if I come up with a value for Q that is lower than the value that I'm given for K, that means that my denominator value is larger than what it should be. So a larger denominator means I have more reactant present in my system than I should if I were at equilibrium. So how do I get rid of reactant? I convert it to product. How do I convert it to product? I favor the forward reaction. So my forward reaction will use up the reactant, right? Decrease the amount of reactant, raise the amount of product, and bring that Q value higher until it hits K, at which point I'm at equilibrium. And that brings us to our third situation. If you calculate a Q value that is equal to the K value that you're given, then your system is already at equilibrium and the forward and reverse reactions will proceed at equal rates. So remember, whenever we're, trying to hit equilibrium, it's not that the opposite process is not happening, right? The reverse or whatever, the opposite process is still happening. It's just happening at a slower rate than the process that is kind of favored until we reach that equilibrium position, at which time both processes will continue, but at equal rates. So it will appear like nothing is happening. This is the same thing here. So the way that I remember this, the Q equaling K is easy. I think back to in elementary school, the greater than less than sign. So if I list it as Q and K, right? And Q is on the left and K is on the right. And if Q is less than K, I think of I'm an idiot, right? Yum, 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 yum. My forward reaction will continue. Will not continue. My forward reaction will be the favored process in order to establish equilibrium. And if Q is greater than K, my reverse reaction will be the favored process in order to reestablish equilibrium. So again, my primitive button pushing brain, that's what I think of. Okay, so now I'm gonna just walk you through mathematical scenarios, and I have these pre-solved, so it'll go quick. So we have this synthesis of ammonia system. We're given the equilibrium constant. So that is the value for K, right? 0.06. Predict the direction in which the system will shift to reach equilibrium in each of the following cases. So we're given these concentrations that may or may not be concentrations that are at equilibrium already. So what we have to do is we need to write a Q expression using the coefficients of the equation. So this would be, ammonia would be squared, nitrogen would be to the first power, hydrogen would be to the third power. And now we're going to substitute that in. Where's my nitrogen? So this is why super important that you have a scientific calculator that can do these, what am I doing? Exponents and things easily for you. Okay, and this value comes out to 1.25 times 10 to the 7th. Okay, so that Q value is much larger than the K value that I was given, right? So what does that mean in terms of like how this was calculated? This number was so huge because this numerator was much larger than what it should have been. So that means I have way more product. I have way more ammonia than I should if my system were at equilibrium. So how do I get rid of ammonia and get more nitrogen and hydrogen? The reverse reaction has to occur. Okay, so predict the direction. So reverse reaction is favored to establish equilibrium. So there's too much product and not enough reactant for this to be considered to be at equilibrium based on this experimentally derived equilibrium constant. Okay, second example, same reaction, right? We're just doing the math again. So the same Q expression. So the setup for this would be the ammonia 2 times 10 to the negative 4th, and that would be squared. And we have for the nitrogen 1.5 times 10 to the negative 5th, and that's to the first power. And then we have 0.354, and that would be cubed. I like to get rid of scientific notation whenever it's like easily done, you know, because it's just less buttons to push on the calculator, to be honest. You know, so like 3.54 times 10 to the negative 1st, I could just do 0.354 and save myself a couple keystrokes. So when this is calculated, this comes out to 0.0601. It's like a long irrational number. Okay, but basically Q is equal to K. So those concentrations, if I had, you know, those concentrations in this system, that system would be at equilibrium. And here's my third scenario. So Q, what's important when you're problem solving and you're doing questions like this is make sure you only say K when you know it's at equilibrium. If you're not sure, Q is always safe. It's just a nitpicky detail, but it could get you a point. Okay, so the numerator would be 1 times 10 to the negative 4th. That's my ammonia squared, divided by my nitrogen concentration of 5. That's the first power. And then my hydrogen concentration would be cubed. And this comes out to 0.002. So Q is less than K because 0.002 is less than 0.06. So what that means is I have a denominator that is larger than it should be and a numerator that is smaller than it should be. So I have too many reactants for this system to be at equilibrium and not enough product. So how do I get rid of reactant and make more product? My forward reaction has to occur. That will allow me to get rid of reactant and convert it to product. So my forward reaction is favored. Make sure you say it that way. Don't say shift. That's juvenile. Boo. So forward reaction is favored in order to reduce reactant, increase product, and establish equilibrium. So those are your three. So that's 7.5 is just understanding how to compare Q and K. The last section here, this is super quick. This is what we're going to look at what you do to K if you manipulate an equation in some way. And this is just like 3 quick examples. We'll do more in class, you know, to practice, but this is just to kind of give you like what you need to do. This is basically it. So if you reverse a reaction, you have to invert K, so it would be 1 over K. If you multiply a reaction by a certain value, you would raise K to that same power. If you add reactions together, their individual K values would be multiplied. And if you were dealing with Q instead of K, the same manipulations would apply. So here's the first example. The equilibrium expression for a reaction is a reciprocal for a reaction written in reverse. So we have the way that it's written here on the left-hand side. Here's our product over our reactants. Well, if I write my reaction the opposite way, my K expression would be written the opposite way, which is just the inverse, the reciprocal of it. Second example, if I have this reaction on the left, the same reaction as above, like the last slide, I could write its K expression. If I took all of these coefficients and cut everything in half, my exponents would all be cut in half as well. So my K value would be raised to the half power. And if I doubled everything, I'd square it. And the last one, because that would come into play if we're doing a Hess's law calculation with K. And last one is if I were adding two reactions together, right, to get a final process, and I'm given their component, I love when it does those auto shapes, I'm sorry, again, simple person. You would have to multiply their K values. So we'll do practice with that. You do have to memorize what those manipulations are, but we'll do practice with it in class. Thanks.